the aim of this talk is to try and give some intuition on how the observation error correlations are interacting with the error correlations in your a priori information. And this is done very much kind of in the variational data assimilation framework, so under the assumption that the errors are unbiased and Gaussian. And this is work that I've been doing with Sarah Dance and Joe Waller, all at the University of Reading in the UK. Yeah, so as you all know, the background error correlations have been known to be important for data assimilation for a long time, and there's lots of kind of efforts into modeling the balances and obviously the ensemble methods. But until recently, observation error correlations have largely been neglected in NWP. So to account for this, we've been using either thinning the data or super obbing, or the error variance has been inflated. So therefore, if we can accurately account for the observation error correlations in data assimilation in an optimal way, it will allow for dense observations to be assimilated, which could be important for high resolution and high impact forecasting, as we've already heard about today. So, so this has motivated observation error correlations to be estimated for a range of observations, and we've now kind of got some different methods for trying to do that. And there's obviously, from Nancy's talk, there's more thought into actually how practically we can make use of this information in data assimilation. So the question that I've been thinking about is, can we expect to see benefits of including observation error correlations in all observation types? Or are there cases when it would be better just to thin the data to the correlation length scales? And because, as we've already heard, that we've got in NWP, we're kind of in the lucky situation when we have too much data. So we have to make these decisions. So there's been various theoretical studies already looking at the effect of correlation observation errors. So yeah, some a long time ago, some more recent. And so one thing that this work differs from previous studies is that we're not looking at the case of a kind of suboptimal R. So I'm assuming that we kind of live in the world where we know exactly what our error correlations on our observations and backgrounds and our observation operator really are. And also, unlike previous studies, I'm going to really concentrate on how the impact of the observation error correlations depends on the specification of the background error statistics. And I won't have time, but I've also been looking at the observation operator. And yeah, so many of these previous studies have kind of shown how the results are sensitive to the background error correlations, but I'm trying to kind of untangle that a little bit more. And I'll also be looking at a variety of metrics, which I'll talk about in a minute. So one result that's really important in terms of understanding this is previous work that's shown that in the case of positive error correlations, the effect of having a correlated covariance matrix means that you end up with less uncertainty at small scales, but more uncertainty at large scales. And this is illustrated with this figure, where my covariance matrix is a circulant matrix with a Saw correlation function. And so here the grey line is an identity matrix, and then going out to the blue, we've got increasing correlation length scale. And then in this plot, we've got the same functions but plotted in eigenspace. And what you see is that at small wave number or large scales, as the correlation length scales increase, the uncertainty increases, whereas at small scales, as the correlation length scales increase, the uncertainty reduces. So this is an important result that kind of needs you to hold in your heads. So the different metrics that I'll be looking at to try and understand this are firstly the analysis error covariance matrix. So for an optimal DA system, we know this can be written in terms of the observation error covariances and the background error covariances and the observation operator. I'll also be looking at the influence matrix, which was presented on Tuesday by Daisuke. So this looks at the sensitivity of the analysis in observation space to the observations. So on the diagonal, you have the sensitivity of an analysis at an observation point to an observation of that same point. And on the off diagonals, you have the sensitivity of analysis at an observation point to a different observation. So the off-diagonal elements kind of tell you about the spread in information from the observations. And again, this can be written just in terms of the covariance matrices of your R and B and your observation operator. And as Daisuke has already mentioned, the trace of this matrix gives the degrees of freedom for signal. So just the sum of the self-sensitivities and not the information about the cross-sensitivities, so the spreading of information. And lastly, I'll be looking at mutual information or Shannon information content, which measures the reduction in entropy due to the simulation of the observations. So this can be written both in terms of the analysis error covariance matrix and the sensitivity or the influence matrix. And in both cases, it's a determinant of these matrices. So, so it tells you about in this case, the analysis error correlations as well as the variances, and then also the self-sensitivities as well as, or the cross-sensitivities as well as the self-sensitivities. So it's a very different metric compared to degrees of freedom for signal. So I've kind of set up the most simple experimental design to really try and understand this. So it's just a two-variable experiment where my B matrix has this form. So beta is my background error variances and gamma is the correlations. And then my observation error covariance matrix has a similar form, where this is my variances and this is my correlations. And yeah, in the interest of time, I'm only going to talk about the case when the observation operator is identity. But we have a paper that's pretty much ready to be submitted, so I can give you more information on that. So to start off with, I kind of wanted to give a kind of graphical interpretation of what's going on. So this is just an example of Bayes' theorem. So in the first column, I have my prior distribution, which in this case is just has a variance of 1 and a correlation of 0.9. And then in the second column, I have a likelihood distribution for 3 different cases. So in the first case, it's the same as my prior. In the second case, I have 0 correlations in the likelihood. And in the third case, my correlations are minus 0.9. So it's kind of just a orthogonal to my prior. And then to get the posterior distribution, we just multiply these 2 functions together and normalize. So what you see quite clearly is that as the correlation structure in your prior and your likelihood become more and more different, the analysis error variance quickly reduces. So we can understand this in terms of the scales that each piece of information is telling us about. So in this case, because we've got positive prior error correlations, the prior has a lot of information about small scales, but less about the large scales. Whereas the observations are able to tell us more about the large scales, but less about the small scales. So yeah, and that combination gives us the most accurate analysis and the smallest region of uncertainty. So we can now look at the different metrics as a function of, so this is the analysis error variance as a function of the observation error correlations on this scale and the background error correlations on this scale. And what we clearly see is that we get this peak in the analysis error variance when the correlations are the same in both the prior and the likelihood. And this is independent of the value of the variances. So in this case, I've got my background error variances twice that of my observation error variances. So again, we can understand this because in that case, both the observations and the prior are telling you about the same scales, whereas if you kind of come out to these regions where we have very different structures in our observation and background error correlations, then we're getting information about different scales, and we're more able to reduce the analysis uncertainty at all scales. And this is kind of corroborated by looking at the analysis error correlations, where we see along this kind of diagonal that then we get close to 0 correlation. So it's been reduced more in all directions. And just to remind you that the analysis error correlations, the sign of the correlations tells you about the scales that the analysis is most sensitive to. So then we can also look at the influence matrix. So this is the self-sensitivities again, as a function of the background error correlations and observation error correlations. And what you see now is there's less interdependence between the background and the observation error correlations. And generally, as the observation error correlations increase, you get larger self-sensitivity, and as the background error correlations increase, you get less self-sensitivity. And this is kind of understood. So the role of the background error correlations is generally to spread information. So in this case, you have more information coming from other observations, so the influence of a direct observation is going to be less. Whereas when you increase the observation error correlations, the information from other observations is kind of reiterating the information, the direct information in the direct observation. So it has more the analysis is more sensitive to it. But we can also look at the cross sensitivities. So as I said before, this is kind of a measure of the spread in the information from other observations. And if we look at the case when the observation error correlations are 0, you see that as the magnitude of the background error correlations increase, you get an increase in the cross sensitivity. So again, this kind of shows that the role of the background error correlations is to spread information. And similarly, if you look at the case when the background error correlations are 0, you get and the observation error correlations magnitude increases, you get an increase in the cross sensitivities again. But what's interesting is that it's different signs. So that means that when the background and the observation error correlations are the same, and we go along the diagonal, we get 0 cross sensitivity. So effectively, the role of the background error correlation to spread information is being kind of counteracted by the role of the observation error correlation. So when we have the same background and observation error correlation structures, we're getting no spread in information from the observations. Yeah, and again, we can relate the sign to the scales that the analysis is most sensitive to the observations. So when we're along this diagonal and the observation and background error correlations are the same, then the analysis is as sensitive to has the same sensitivity to the observations at all scales. And lastly, we have mutual information, which, as I said previously, is kind of a summary of all of these figures. So we see that we've kind of got this general pattern of larger observation error correlations mean more information in the observations, and larger background error correlations meaning less information in the observations. But then we also have this the peak in the information content occurring when the backgrounds and the observation error correlations are very different. So kind of the motivation of this was to understand what this means in terms of data thinning and how we should choose when to use dense observations with correlated errors and when not to. So for this, again, a very simple experiment where I have a circular domain discretized into 32 grid points, and my R and B matrix are given by circulant matrices with correlation functions given by the SOAR function. And in these experiments, my background error correlation will be fixed at 5, the length scales as 5, and my observation error correlation length scales will vary. And just to make the figures look slightly nicer, the observation and background error variances are both set to 1. And again, I'll be using direct observations of the state variables. So this figure shows on the left, we have the trace of the analysis error covariance matrix, so just the sum of the variances, as a function of the thinning distance between the observations. So what you see in each of these lines is that as you increase the thinning distance, so reduce the number of observations, the trace of the analysis error increases as you'd expect, less observations, less accurate analysis. But what you see in the different lines is that these are different observation error correlation length scales. So we get a peak in the analysis error variances when our correlation length scales in our R matrix, so in our observations, is the same as in the B matrix. And then this reduces as you either increase or decrease them away from the B matrix. And then the second plot shows the mutual information divided by the number of observations, again as a function of Finnan distance. And what you see, so this is kind of a metric of the efficiency of the system. So it's the average information content of each observation. So what you see now is that when the length scales in R and B are the same, that this metric is insensitive to the thinning distance, and that can be related to the effect on the influence matrix. But when you have correlation length scales smaller in your R matrix than in your B matrix, you find that increasing the thinning distance increases this metric. And that kind of makes sense because you have more, because of the role of the background in spreading the information and the fact that the correlations in your background means that you have the small scale information. It's kind of redundant to have dense observations. Whereas if your correlation length scales are much larger in R than in B, then you have much smaller scale information coming from your observations than is available in your background. And that means that in that case, it's much more beneficial to have dense observations. Yeah, so these are my conclusions, which I guess I can let you read. Am I out of time? Or? Yeah. Oh, no, OK, great. Yeah, so the main kind of take-home message is that the impact of observations with correlated errors can't be understood in isolation of the background error correlations or the observation operator, which I've left out of this talk. And this is particularly true if you're interested in the impact on analysis errors and spreading information. And we find that when the correlation length scales are very different in the observation and a-priori errors, and it doesn't matter if the observation error correlation length scales are longer or smaller than the background, but as long as they're different, we get the greatest reduction in analysis error and the greatest spread in information from the observations. And the idea is that hopefully this kind of information might be useful for designing perhaps new instruments, but also observing networks. So I gave the example of data thinning. It's found that dense observations are most beneficial in terms of my metric, my mutual information divided by number of observations. It's most beneficial when the observation error correlation length scales are larger than in the a-priori error correlations. Okay, thank you.